record and then ask, how about homework? How's homework going, folks?
Better than it was.
Better than it was? Okay. Been helping a few folks troubleshoot. If things are not working, check your spelling and your capitalization. If you are working in SAS or Stata or R, capital versus small letters has been one source of issues we've found so far. Anyone want to ask questions about homework since we're all gathered here? Deb reports great success with the empty model. Excellent. That's no small task to be able to look at something that used to be a challenge and you're like, I got this now, right? So we call that mastery learning. Do it enough times, eventually you can do it. Well, let me know if you do have questions. I'm happy to try and provide advice and or troubleshooting. Let's see. I pulled up the schedule. I do not have anything yet up for next week, but I will have something done soon. So we will have a review opportunity. Nothing new, just another type of data set to practice on. I have, in addition to the examples that I'm building in class, I want to point you towards your textbook, by the way. I deliberately did not use any of their examples so that you would have another set. So that is another place you can go to get more examples of how things would work. And they explain things a little bit differently than I do, which is always good to hear it from different perspectives so that you can become fluent in other people's languages. Otherwise, then next week we have an exciting new chapter, the idea of moderation and interaction terms, which is honestly one of my favorite things to teach. So maybe I'm more excited than everyone here, but I think it's fun. So we'll get to do that later. But if you don't have any homework questions, then maybe we can talk about lecture 4. Does that work? Why not, right? So this unit, we're talking about the idea of unique effects. That's the new concept. So what happens when we put together multiple predictor variables at the same time? How do we think about how to interpret their slopes, as well as how do we characterize effect size? That's what we've been talking about. So, I don't know where I want to stay. Yeah, this. Let's do it this. Slide 10. So the basic idea in trying to describe the contribution of multiple predictors to the same model predicting an outcome is that we want to pay attention both to their joint efforts but also to their unique efforts. So the R-square for the model, which we talked about last time, 2 interpretations. R-square is proportion of variance that's been explained. You can also think of it as the reduction in the residual variance relative to the empty model. And R-square is also the square of the correlation between your actual outcome y and your predicted y hat, not to be confused with theta hat, but y hat. That would have been a funnier hat, I think, but no one asked me. So that's one thing that we're concerned about, is sort of how well does the model work on the whole? And what's nice about that concern is that all of the efforts of the individual predictors get counted. So we're counting both their unique contributions as well as their common contributions. So do you remember this picture, these diagrams here? Should we go back over this, or we got this? What do you think? Again? Why not, right? Yeah, so this idea here, this Venn diagram, or Ballantine as it's known, is a way of describing the partitioning of variance in an outcome. So y is my outcome variable. That's to be predicted. x1 is one of my predictors and x2 is another. So within this diagram, the area that is labeled A here is what x1 brings to the prediction of y that x2 does not. Not all of x1, so there's only some overlap. There's some of x1 that has nothing to do with y, which would be this part out here. B is the area that only x2 brings to the prediction of y. C is the area that they have in common. So this C common area does get included in the model R square, but only once. So one contribution of common rather than two. But it does not, area C does not get included in determining what each predictor's unique contribution is. So what does each predictor bring to the table uniquely? That's what its slope or slopes is supposed to describe. And then E is what's left over, because in most cases with real data, Y is not going to be predicted perfectly. So E takes it describes the amount of variability that is left over that is unrelated to any of the predictors or what they have in common. So we're interested in testing the significance of A, B, and C together, the significance of R squared. How do we do that? How do I answer the question, does my model significantly account for variance? Feel free to read from the screen.
F-test? Would it be the F?
Yeah, F-test, yeah. So F, as a general principle, is a significance test for multiple slopes at the same time. In your formative assessment, some of you wrote about F as a difference in variances. It could be used for that, but that's not the context that we're talking about here. F is used to test multiple slopes at the same time against a null hypothesis, usually of 0. And F is in squared units because we want positive slopes and negative slopes to not cancel out. So it is a multiple variable generalization of T, which is estimate divided by standard error. It's basically the squared version of that for multiple slopes, their standard errors, and what their standard errors have in common is also part of the formula for that. So that's one question then. Does our model significantly predict our outcome? And then the next piece then is, what about A, B for each of these predictors? And we want not just significance, but also effect size for that. So then we started talking about different ways of generating unique effect sizes. So the word unique, give me some synonyms for that. When I say unique, what do I mean? If I say that the slope's unique effect is 2, it's the effect of the predictor, what? How else would you say the idea of unique? Controlling for the amount that each one contributes, yeah. Controlling for, adjusting for, after accounting for collinearity, which is the idea that your predictors are related. So there are several synonyms that people use to get to this idea. This is slide 11 where I have a couple of them. To me, the word unique is the quickest and easiest way to say the effect of x1 controlling for, or partialing out, or holding constant. So all of those terms you can think of as synonyms for the idea of a unique effect. And fortunately, just like we had for a variables bivariate slope, we'll get an estimate, a standard error, a t-test statistic, and a p-value that tells us whether that unique effect is significantly different than the null hypothesis of 0. The tricky part, though, is the effect size. Let me go back then. So different ways of doing effect size then. We want to provide effect sizes for a couple different reasons. We want to talk about that again? That'd be helpful, maybe? A little bit? Yeah. So significance depends on two things. One of them is effect size, and the other is sample size. So we can't just say, I have a significant slope, the end. And I can't just say, I have a significantly positive slope, the end. Because it could be the case that I have a very weak relationship, but a lot of power to detect it, and that's why it's significant. Or it could be a strong relationship with medium power, or some combination in between. So we want to be able to convey the absolute size of a predictor's contribution. We can't do that just by staring at the slopes. So if I have one predictor that has a slope of 2 and another predictor that has a slope of 3, I can't look at those numbers and say, well, 3 is more than 2, so that one's more important, because it depends on what 3 refers to. So if a slope is 3, that's a change in y per what? What's the end of my sentence defining a slope? Slope is the change in y per what? X. 1 unit change in x. So unit is the key here. So that means that if I have a variable that's in dollars, that's going to be a different slope than a variable that's in euros, or thousands of dollars, or anything else. So the slope that is attached to a predictor where the slope is 3 instead of 2 could be just a function of the fact that the predictor has different units. So we can't just look at the unstandardized, meaning just the slopes that get spit out, and use them to ascertain which slopes are relatively more important. We need to put them all onto the same scale in some respect so that we can talk about their relative importances next to each other. And there's different ways that one might do that. Standardized slopes is one option, although they are not as useful as some alternatives. Then we have the different types of eta square or eta, which is the same idea as R, just by a different name. And we also have R square versions too. So that's where it gets confusing, is that effect sizes can come in an R metric, which ranges from -1 to 1. They can also come in an R square metric, which ranges from 0 to 1. And beyond that, there's differences with respect to what goes into the denominator. What is it the effect relative to? So we can go back over that today, since we did a little bit of that last time. So this is, let's see, about standardized slopes. Standardized slopes are easy to get. They're potentially problematic in that people want to talk about them as the change in y for a standard deviation change in x. But in reality, the amount of variability in x that goes into the prediction is not its full variability, it's its unique variability. So really, we would need the standard deviation of the part of x that it brings to the table by itself, which is not what the standardized slope tells you. So we're not going to put as much focus on those for that reason. We talked about semi-partial versus partial. So this one, semi-partial, has a synonym that is known as part, unfortunately. I did not make this up. This is a ratio of the amount of sums of squares, the amount of information captured by a predictor relative to the total. And I like semi-partial eta squares. This is my favorite because it's the easiest to explain. Semi-partial eta square, or abbreviated this SR square thing, tells you how much of the model R square is because of that predictor. That's what it means. So it's directly intuitive with respect to how much that predictor contributes to the model's level of prediction. It's in the same metric. So for instance, if I had an R square for my model of 0.2, what would that mean? So if my model R square is 0.2, what does that number tell me? I explained 20%. And if I calculated a semi-partial eta square, yeah, explains 20% better than an empty model, yep. If I calculated a semi-partial eta square for this predictor right here, and I found that it was 0.1, what that tells me is that, well, 10% came from x1 out of the 20 that I have. So x1 is responsible for half of my explained variance in that scenario. So it's taking the model R square and carving it up into pieces and saying how much of it is due to this predictor, how much is due to that predictor, and the rest is going to be some function of common. So I like this one. Because it's out of total, semi-partial eta squares are comparable across models that have different combinations of predictor variables. So that's another reason that it's useful. So if I want to talk about the relative importance of a predictor to a model, then I can use this, and it's pretty straightforward. Okay, how are we doing so far? Thumbs up? Thumbs up, okay. A non-representative sample of the class has thumbs up me. I say non-representative because you can select whether to put your thumbs up and to have your cameras on or to be in person. And there's all kinds of reasons why people might choose to have a different experience. So partial then, what's this thing? This one is harder to explain. It's easier to find, though, because this is the thing that you're currently getting practice on. In homework 4, I'm asking for partial correlations, which come from your t-test statistic. So in example 3, I spent, let's see, what day was that? Oh, would have been Saturday or Sunday, so fairly recently. I updated the files for example 3 to show you how to do these calculations within the program themselves. So within each of the programs, I have additional code that allows you to take that t-test statistic that's stored and convert it into an R. The only thing that you might have to change is denominator degrees of freedom if you're using SAS. Otherwise, it's built into the code that I gave you. And in the previous homework, you got a chance to practice doing Cohen's d the same way. So these are easy to get. What they mean is a little bit trickier. So if we take our R that comes from this and square it, then we're in partial eta squared as a metric, or PR squared as it's abbreviated in your textbook. And it's how much sums of squares the predictor got out of that plus what's left. So this is not directly related to the model R square. It's setting aside what happened with all the other predictors in the model and just focusing on this one relative to the error term. So I find this one more confusing to explain because of that, because it's a different denominator. Because everything else that's in the model is not part of this, you can get greater partial R squares if you add extra predictors to your model that reduce E-variance. So the same effect can look bigger in a model that has a stronger prediction. So it's harder to compare these across studies for that reason. So the strategy that I think makes the most sense, sort of trying to put all this together, is for each predictor conceptually. So do you remember what I mean by conceptual predictor? The idea that any one predictor might take multiple slopes to describe its effect. So for instance, in homework 4 right now, I'm asking you to look at the effect of screen time, but I asked you to divide it into children who are below recommended amounts versus above recommended amounts. So it's 2 slopes. So what I want to be able to show you today is how to get like a semi-partial eta square for 2 slopes at the same time, to lump them together to talk about one conceptual predictor. So I'll show you how to get semi-partial eta square for each conceptual predictor. And it's super easy if the predictor is described by 1 slope. It's a little more complicated if it takes more than 1 slope. So I think that that's useful because that tells you how much of the R square that predictor is responsible for. With respect to each individual slope, though, then you can report effect sizes in one of these 2 metrics because that corresponds directly to that slope's t. You're not talking about how much of the R square it's responsible for. You're just trying to give it some way of describing that slope in a standardized fashion. So both semi-partial eta square to describe the contribution of a predictor to the model R square, partial R, partial eta, to describe what happened for each individual slope. So when you see the letter eta or the word eta, think R. When you see the word eta square or the symbol for it, think R square. And they're related to each other just as you would think. How do you take an eta and make it an eta squared? Not a trick, I swear. How do I take an eta and make it an eta squared? You square it, exactly. How do I take an eta squared and make it an eta? Unsquare it. Square root it, yes. I'm getting practice on that, by the way. As a Midwesterner, the correct pronunciation, in my view, is square root. And I've noticed that this is a dialect thing, that to some people that sounds horrible, but to me that sounds perfectly acceptable to say square root. Like I go up on the roof and I drink root beer and I calculate square roots. That's what I do. But to prevent people from cringing openly, I've trained myself to say square root, even though that sounds wrong. But unsquare it also works. We'll take that. So in your textbook, for instance, they use this terminology of semi-partial correlation and correlation squared. In all of the output across the programs, they call it eta and eta square. I don't know why they have to be extra confusing, but I want you to know that it is the same thing. D is a different animal. So when you see D that has nothing to do with R or R square in terms of the metric, D is in standard deviation units. So D is useful for predictor slopes that convey group differences. And there's no such thing as a semi-partial D, only a partial D. So then interpreting these things, we had one example here that we did, and then I'll show you a more complex version. So this is, this is slide 25 in lecture 4. So this is a simple example, meaning that everything that you would want to know is going to be really easy to get out of software directly. And this is the type of example that your textbook starts with. So in the order that they do in their chapters, they decided to jump into these models almost right away. And in each of those examples, though, their predictors are described by only one slope. So they're going about this from a different perspective than I am. But I have a reason why I want to do it my way, because it's a separate issue in terms of how you lump things together and why. So here's an example. If I have two predictors, this is from example 2. So we're predicting income, and we did it separately from education and separately from marital status. And in each of those models, here are the R-squares that we got from one predictor at a time. When I put them together, what I found, and what I'll show you, I think, did we go over this output? I can't remember if we did or not. We did? Okay, we did that much. Good. The R-square from the model with both of them together is 0.19, which is actually a little lower than what it would be if you just added these two together, and that's because they're correlated. So you can expect a smaller R-square from the joint contribution because you don't get to count all of the common variance twice. You only get to count it one time. So I can look at a significance test that's directly provided on my output to talk about what happened to beta 1 and what happened to beta 2. But to characterize their effect sizes, then, here's what it would look like. And I'll show you where I got these numbers. So for education, semi-partial eta square is 0.1396. So the way that I would talk about that number is that the R-square for the model is such that I got 19% of the variance. 14% of that came from education by itself. So education is doing most of the work with respect to capturing prediction of income. Out of the 19% we got, education did 14 of it. The partial version of it is higher, because the partial version is talking about what proportion of variance education got that marital didn't. So setting aside the contribution of the other predictor, this is how much of the residual that it explained. We can do the same thing for marital status. Its semi-partial was 0.04. So 4% of the model R-square is due to marital status, and it's a little bit higher if we do the partial R-squared too. And in this case, the reason that I say that this is a simple case is because there's only one slope to describe the effect of each predictor, and so I can easily ask for partial correlations and semi-partial correlations using built-in routines in my software that will give that to me. I don't even have to go to the work of converting my T into R, I can just ask for it. So in Stata, I think it's P-core, if I remember correctly, or P-C-O-R-R. In R, it's core test, and SP core test. And in SAS, it's proc core. You can ask for partial and semi-partial correlations directly. All right, how are we doing so far? 2:30. Slow nods. Any that you want to hear again or hear differently? Yeah, go ahead.
If we have more variables like education, marriage, or age, so if we have three predictors, we can also directly compare the semi-pressure R-square also.
Mm-hmm. Yeah, if we added a third variable in here, then that variable's semi-partial R-square would talk about how much of the R-square it was responsible for. Yep. Yes, indeed. Now, what about a more complex case? So this model of education here, when I put in education right here and I give it one slope as such, what kind of relationship am I saying that education has to income? Looking for a one-word answer, starts with an L. Linear. Yeah. So a 1-unit increase in education has a beta 1 increase in income. Doesn't matter if it's going from 8th grade to 9th grade, or going from 11th grade to 12th grade, or going from 19th grade to 20th grade. Now, that's probably not true. And in fact, we found that a model was more useful if we split education into 3 slopes. So we talked about the effect of education amongst people who didn't finish high school, the boost you get from graduating high school, and then the additional boost that you get from pursuing education past high school as 3 separate pieces of education. And in that model, we captured about 16% of the variance in income all by itself. So this is from example 3, where each of these conceptual predictors was fit in a separate model. So the last one here was piecewise education, and the F for the model, in this case, is the direct answer to, is education a significant predictor of income? The F for the model tells me about the 3 slopes combined that it takes to describe the effect of education. Likewise, we fit linear and quadratic effects of age in predicting income. So the F for the model for those 2 slopes directly answered the question, is age a significant predictor of income? And it took 2 slopes to describe how age relates to income. The first model in that handout was a 3-category grouping variable, whether respondents rated themselves as lower, middle, or upper class. And because it's 3 categories, I need 2 slopes to differentiate those 3 categories. And the F for the model directly tells me whether working class as a conceptual predictor is related to income. So this unit was designed to get you used to the idea that sometimes it takes more than one slope to fully represent the contribution of one variable as an idea. Like education is the idea. The 3 slopes are how we describe how education as an idea relates to income. Now we want to be able to put together all three of these predictors into the same model, and we can do that, even though each one takes more than one slope. So conceptually, it is not different than this previous slide, where we put two predictors in the same model. This is three predictors, even though it's 7 slopes. So beta 1 and beta 2 are for the effective working class, the grouping variable. Beta 3 and beta 4 are for the linear and quadratic slopes of age. Beta 5, beta 6, and beta 7 are for the sections of education. So conceptually, to me, I have 3 predictors in my model, 3 ideas. One takes 2, the second takes 2, and the third takes 3 slopes. Previously, when each of these conceptual predictors was in the model separately, we didn't have to do anything to figure out whether that predictor had a significant effect, because the model R² told us that. That's the effect size and the F that goes with it. Now we have to do something extra, because what I want to know is how do beta 1 and beta 2 work together to contribute to the model R²? How do beta 3 and beta 4 work together? How do beta 5, 6, and 7 work together? So separately, if I add the R² from each of their contributions in separate models, the total would be 38%. But when I put them all together, the total is actually much less. It's only about 29%. Because these 3 variables are correlated with each other to at least some extent. Okay, how are we doing so far? So here's what I found, and then I'll show you how I found it. Together, beta 1 and beta 2 accounted for 4% of my model R². That's my semi-partial correlation squared. So they got 4.28% of the variance explained out of the total here, which was 29%. So this is the contribution of working class over total. That's what semi-partial eta² tells me. What proportion of variance in income is attributable to those 2 slopes? Now, how would I know if that's significant? In my output, what will I get for beta 1? What's going to show up just from running the model without doing anything separate? What shows up for each slope?
P-value?
P-value. So if we start from the columns from the left-hand side of the output, there's an estimate column, otherwise known as coefficient. Those are synonyms, meaning the best answer for these data that made the residuals as small as possible. Next to that is its standard error. Cough, cough, homework question. What's a standard error for a slope tell you? What's a standard error for a slope tell you? How far off the slopes are from what?
Could be the null. Or,
That's T. Yeah, standard error is the average distance of a sample slope from the population slope, otherwise known as the expected inconsistency across samples in what you'd get. Yep. So estimate divided by standard error, that next column over is T. And that tells you how many standard errors away from the null hypothesis you are. And then next to t is p, which tells you the probability of observing a slope that extreme if the null hypothesis were true. And if p is less than 0.05, if it's less than 5% of the time we'd see that result, we say that that is significant according to our cutoff for alpha. So I'm going to get that set of results, estimate, standard error, t and p, for beta 1 and for beta 2. And that tells me whether, specifically in this context, the definition of beta 1 is how the middle group differs from the low group. Cough, cough, homework question. I have to say it that way. How the middle group differs from the low group, because it's always how the 1 group differs from the 0 group. Otherwise, the direction is backwards. So if the slope is positive, the 1 group is higher than the 0 group. If the slope is negative, the 1 group is lower. So I can find out whether middle differs from low via beta 1. I can find out whether upper differs from lower via beta 2. I can find the difference of beta 1 and beta 2 to get the difference of middle versus upper as a linear combination. But none of that gives me a direct significance test as to whether beta 1 and beta 2 work together. So the good news is that you don't have to learn anything new as a concept. We need our friend f. F is what we use to lump slopes together. So in this case, I have an f for the overall model that tells me, do the 7 slopes work together to predict income? And the effect size that goes with all 7 is this r square of 0.28. Now I'm divvying it into pieces. So I need an f for beta 1 and beta 2 together to answer the question, does working class have a unique relationship to income after controlling for age and education? I've got an effect size for this, but I need to get an f2, and I'll show you how to do that. It's one more line of code. Likewise, beta 3 and beta 4. Question? Or just stretching? Just stretching, okay. Beta 3 and beta 4, same exact concern. I can get their semi-partial eta squared, it's 0.08. So age is responsible for 8% of the variance in income uniquely. I need an f to judge the significance of the two together to tell me whether that semi-partial effect size is significant. Last but not least, education takes 3 slopes. So I need another f for that. The 3 slopes for education caught 8% of the variance. So about the same as age, just a little bit under. So this is the one new piece of coding for this unit, the idea of dividing up your model results into the sections that map onto different conceptual predictors and getting significance tests and effect size for those sections, in addition to just for the overall model and per slope. So this is like a middle ground. All right. How are we doing? Okay. Questions or things that I can say again or differently? All right. So it turns out that if you want to talk about each of these 3 conceptual predictors, working class, age, and education, as an effect size, for semi-partial eta squared, lumping them together is not only helpful, but completely necessary. If I were to try to compute semi-partial eta square for each slope, in this case, I'm not going to get the right answers. So by the way, this model the idea that we have both a grouping variable as a predictor, so working class, as well as quantitative predictors. In another class, this might be called analysis of covariance, or Ancova. So Anova is when you have a categorical predictor. Ancova adds what they call covariates, which means quantitative predictors in addition. So I have to be careful in these sorts of situations when I look at per slope effect sizes. So beta 1 and beta 2, I could compute a semi-partial eta square for each of those, and if I try to add them together, I'm not going to get the right answer because they share a common reference group, which destroys the orthogonality of being able to add them together. So I can't manually do that. I have to ask the program to do it because the program understands the common reference idea and it factors that into the calculation of the sums of squares. So I can compute per slope effect sizes for beta 1 and beta 2 that refer to partial correlation or partial D, but I can't relate those back to the amount of the R square. I have to lump them together to do that. Likewise, age. Homework question from homework 3. So a throwback, if you will. Isn't that a thing, Throwback Thursday?
Yeah.
Or is it Throwback Tuesday?
Throwback
It's Thursday?
Mm-hmm.
Oh, awesome. I'm on point then.
Hey.
Me and my Theta hat. We're going to have Throwback Thursday. So beta 3 and beta 4 here. I can't just talk about beta 3 as the linear slope. I have to condition it. This is the linear slope specifically when this variable is 0 because of its squared term right here. So this is the linear slope at 18 specifically. And what happens to it is that it goes up and it starts to come back down. So if you think about the linear slope as being instantaneous to a point, beta 3 is this one at age 18. So if I decided to center age at a different place, let's say I centered it at 50, can I do that? Sure.
If you want.
Sure. Can I center it at 107? Sure. Whatever I want.
Yeah.
It just changes the interpretation of what the intercept means and what the linear slope means in this case. It's specific to whatever you called 0 as your centering point. So if the slope is specific to 18, what do you think the effect size is going to be? Specific to 18. So it becomes problematic to think about effect size when it's conditional like this, because you have to keep in mind that it would be different at any other point. And the same thing is true with respect to the slopes for education. We can't add together their semi-partial eta squares and get the right answer because they're correlated with each other. So what I want to show you is a compromise, lumping together the slopes that go with one conceptual predictor and getting a semi-partial eta square that talks about that conceptual predictor's contribution to the model, and showing you how to talk about per slope effect size that has nothing to do with model R square. It's just talking about its unique effect. There. Here's how we do it. Hat. Nerds just want to have fun, man. I think theta hat would have been more, or y hat would have been more like general,
Yeah.
but this was like a conference for people who do psychometrics, and theta is like their bread and butter, so
Makes sense.
it's like an in-crowd thing. But anywho. So how to do this? It depends on your software. And for those of you who are using SAS, you're welcome. This is way easier in SAS than anything else. Part of the reason why I still use it. Because it just works, and it's nice and easy, and I can make it work. So in SAS GLM, I'm going to add one option to the model line that's going to get me all of my effect sizes for any per slope predictor. Semi-partial eta squares, partial eta squares, and the omega versions, which are analogous to adjusted R-square that correct for small sample sizes. To get custom f-test, so anytime that I want to lump together a subset of slopes, such as to lump together linear and quadratic age to test the effective age, that's going to be a new statement you have not seen yet called contrast. So contrast is used to get custom f-tests anytime you want. There is going to be a reference to SS3 on your code that I have skipped up to this point. That refers to what type of sums of squares. And that has to do with how the predictors get credit when they're entered into the model and whether the ones that were there first get credit for the common part. That's rarely appropriate, so we're sticking with type 3 for that. So in SAS, this is going to be like 2 lines of code and you get everything. In Stata and in R, we're going to have to work a little bit harder. So pcore in Stata and the R package ppcore can both be used to spit out semi-partial and partial etas and eta squares for one slope at a time. So if you have a conceptual predictor that only takes one slope to describe its relationship, then this will be fine. These packages cannot be used to add slopes together, though. So to do that, we're going to have to do a workaround. The statement in Stata to get custom f-tests for groups of slope is called test. In R, we can use GLHT, which is something you've already learned, and it will look a little bit different, but it otherwise works the same way. So I'll show you how to do that in example 4a. So for SAS and Stata and R users, if you want to get semi-partial eta squares for a group of slopes, this is what we're going to have to do. We're going to have to start with the full model, get the sums of squares for the model. We're going to call that SS full. Then we're going to re-estimate the model taking out the predictors that we want the test for. So what would the sums of squares for the model be if these 2 slopes weren't included? We need to figure that out. And the difference between what the full model and the model without them is what I'm going to call sums of squares test here. And then that becomes the numerator for your semi-partial eta squared. So we have to do this manually, take the slopes out of the model to see what the hit is to the sums of squares to figure out what their contribution would be. And we'll do this for every combination. So this process aligns itself with what is known as hierarchical regression or stepwise regression, where you start with like some slopes and then you add in another block of slopes and you look at the change in the R square, and then you add in another block of slopes and look at the change in the R square. This is kind of that. So on your next homework 5 that is not yet available, I'm going to have you do things in a stepwise fashion so that it's fair across programs how much work is involved. Because otherwise SAS users get off way easy in that unit. Because if you start with one predictor and you get the model R square, and then you add another predictor with multiple slopes and you get a new R square, you can just take the difference and you know that that's how much the slopes had to be accounted for. So it's analogous to this process right here. So this is what we'll have to do in software to get lumped combinations of slopes to get effect sizes for the semi-partial eta squares. All right. So to make this a little bit more concrete, here's an example. So this will be the type of process that you'll get to do on your next homework. Let's say that I start with my empty model and that the variance of my outcome variable here is 200. Cough, cough, empty model question. That tells me, on average, how far off each individual is from the mean squared, right? That's variance. So 200 describes the variability in my outcome, all that there is to be had. That's as much variability, and my goal is to make it go down. If I only have an intercept in the model, then the R square at this point is 0. I haven't explained anything. 200 is what I have. 200 is what I still have after I fit the model. Now let's say that I add one slope, we'll call it A. And after I add my slope for predictor A here, let's say the residual variance goes down to 180. So I've computed that relative to the 200 we started with, this is a 10% reduction. The last column is tracking each sequential progress through the models. So because we're talking about a reference point of 0 for the first model, the change in R² between models is also 10%. So this is like what we did in example 2 and what you did in homework 2 with one slope at a time. Now if I want to know if that R² of 10% is significant, how can I find that out based on the output for A here? If A is one slope. This was your first formative assessment question from Tuesday. Throwback Tuesday, too. P-value for the slope, right? Could I also look at the p-value for the model? If I have one slope in here? Yeah, would those p-values be any different? No, they would not. Because the t-test for the one slope, square it, that's your f for the model. So if I only added one slope, then any change in the residual variance has to be due to that one slope. And so I know right off the bat if that change is significant, because I know if the slope is significant, and it's a one-to-one correspondence. So if I keep predictor A in the model, and I add in a slope for predictor B. Let's say predictor B does an even better job. It reduces the residual variance down to 140, which if I have 140 left out of 200, that's a reduction of 30%. So relative to where I started with the empty model, A and B together have explained 30% of the variance. Now what do I do to find out if that 30% is different than 0? Do I have to do anything special? Or can I just stare at the output that's given to me? I can stare at the output. Because the significance test for this A and B together, that's the significance of my model. So that's my f for the model. There's the R² for the model. That shows up automatically, don't have to do anything special. That will tell me, is this 30% different than 0? Do A and B work together to significantly predict this outcome? And how good is that prediction of them working together? It's 30% good. Now if I go over to this column, now I'm tracking incremental progress. So before, just from A, I got 10% of the variance. Now that I'm up to 30, that's an increment or a change in the R² of 20%. How do I know if that jump from 10 to 30, the change of 20% here, how do I know if that's significant?
P-value?
Which one? Yeah, p-value. The answer to is it significant is always p-value, but there's like 12 of them. So that's the catch, right? Which one are you staring at? Which p-value?
For B alone?
For B alone, yes indeed. If this new slope is significant, that means that the change in R² that resulted from adding it has to be significant. It's a one-to-one correspondence. We did this, by the way, in looking at linear and quadratic age. We had a model where we had linear age as A, and then we added quadratic age as B. And in that example, I asked you if the change in the R² due to B was significant, and the reason we know that is the slope for B. So if we add one thing, one slope, and that new slope is significant, then whatever change in the R-square it created has to be significant. It's a one-to-one correspondence. So then if I had both of these things in the model at the same time, the other way that I could get this same information is by temporarily taking B out and seeing what's left. So you end up at the same place with respect to the semi-partial R-square if you add in things sort of stepwise than if you like have it all together and take it out. Now that equivalency changes the more stuff you add to the model though, which is why I don't generally recommend this process. To me, you dump everything in, and then you can compute your effect sizes out of the whole model. But this is very common, so I want to make sure you understand the logic. So now here's the tricky part. Let's say that we add a predictor that is a 3-group predictor, such that it takes 2 slopes to differentiate my 3 groups. So now I'm adding 2 things. Conceptually, it's just one idea that I've added. I've added group as a concept, but group takes 2 slopes. Let's say that group further reduces my residual variance down to 80. Relative to where I started at 200, that's a 60% total reduction. How do I know if that 60% is different than 0? Where do I look? If the R-square for the model is 0.6, what's my corresponding significance test for that? F. Yep, the F for all 4 slopes. So the F for the model is going to lump all 4 slopes together. That's answering the question, do the 4 slopes work together to significantly predict my outcome? So I'll get a yes or no answer to that. And then here's the corresponding effect size. How well do they work together? 60% well. Now the last part. Upon the addition of adding slopes C and D here, my R-square for the model jumped from 30% to 60%, which is a stepwise increase of 30%. How can I know if that jump of 30% is significant? The change in the R-square from adding C and D. This is the new piece that we haven't done yet. So I have to write an extra statement to ask for an F-test that is lumping together just C and D. And that will answer the question, what do they bring together to the model as the change in the R-square after adding them? And here's everything I just said. Because I don't want you furiously scribbling, I want you listening as much as possible. That's why I write everything down. So the step from 3 to 4, this is what you haven't learned how to do yet in terms of judging significance and effect size for the joint combination of the 2 new slopes. So that's a contrast statement in SAS that gives you both an F and an effect size in one fell swoop. The F part comes from state of test, and you got to do the math yourself to figure out what the sums of squares would be without that new contribution. In R, you can use GLHT to get an F, but you got to do the math yourself to figure out the new contribution via sums of squares. So I've got 2 examples then I'll show you how to do that. One of them is example 4a that we started last time. All right. So let's look at that then. Before I close out of this PowerPoint, questions on any of these numbers or concepts? I just made this shit up, right? This is not from any output. I'm just using easy numbers to judge with an example. I'm allowed to make shit up. I have a PhD in everything. Okay. So this is, I promise, the last time you're going to see this example. We are no longer, after today, going to predict income in the general social survey data set. I know. Try not to be sad. So we've been over this code a lot of times. But just to remind you, when I'm working with analyses, I will do all of the predictor making in one step rather than doing it in pieces. That way I only have to run one step and I can recreate the data set as I need. So I am doing in each program everything all at the same time with respect to making my predictor variables. And that's all code that we've seen before, and you've gotten a chance to practice in homework. So the new part then, here's the R, is the model lumping these things together. So model 1 we went over last time. This is the easier case because we had linear education as one slope and binary marital status taking one slope. So when you only have one slope in the model, you can directly get its contribution via effect size in SAS. That's the magic new command that we're adding here. P-core in Stata. So for those of you working on homework this week, this will give you your partial correlations, by the way, P-core. For any slopes that are in the model, you won't be able to use this to get linear combinations. So slope difference effect sizes you have to do extra work for, but these can be done this way. And in R, it's P-core test for partial correlations and SP-core test for semi-partial. And I'm taking those and squaring them so that you can get the eta squared versions. So this is the output that corresponds to the math on this one. Slide 25 with linear education and binary marital status, all those numbers came from this. So I've got each package here so we can review where the new information is coming from. So in this model that has linear education and binary marital status, here's the F for the model. In SAS, 2 slopes, my F is 85. So yes, the 2 slopes do work together to significantly predict income. How well do they work together? 19% well. You're used to seeing this table right here, which would describe what happened for each specific slope. So the slope estimate, standard error, t-value, p-value, confidence intervals. Here's the new piece in SAS. So there's these new tables. There's actually a whole bunch of new output. I just cut it down to what we needed to look at specifically. So there's 2 columns for total variation accounted for. And then there's partial variation accounted for. And so under the total umbrella are these 2. Semi-partial eta square and semi-partial omega square. Omega square is the version that corresponds to adjusted R square instead. But this is the version that we're working with. So this number is how much of the R square this variable, this slope got, 14%. Marital status got 4%. On the whole, 19%. So some of it is what they have in common as well. All right, so this came in SAS just from adding this one word, effect size. Stata folks. Here's your model table that you're used to seeing. So there's the 2 slopes for the model. There's your F for the model. Here's the effect table that you're used to seeing, the solution for the fixed effects, as I call it, the slopes and intercepts, their standard errors, T and P. And then this is the new output that came from P-core, where I've got, note the order here, partial correlations first, followed by semi-partial correlation, followed by partial correlation squared, which is that number squared, followed by semi-partial correlation squared, and significance value. This will match. So the slope for Mary, the significance test for the effect size for that slope is a 1-to-1 correspondence. So we don't have to worry about testing effect sizes for significance because the model already did that. So the only trick with Stata is making sure you're looking at the right column. For your homework, I asked for partial correlation, which is the first column right here. Now, R folks. First thing I asked for was Anova Output, just to get the residual variance. Here is the table of fixed effects that you're used to seeing. Underneath are the words that summarize the model f-test and their R-square. And then this is the output for partial R and semi-partial R that I got out of the P-core, what is it called? Yeah, P-core test and SP-core test package, right there. So this is all straightforward because each slope represents its own separate predictor. And here's what happened across the two, as well as a comparison of how their effect sizes changed when they were by themselves versus together. Now here's our current example with 7 slopes. Can you imagine, like on the first day of class, if I had showed you this equation, what you would have said? Yeah, I'm going to drop this class is what you would have said. But no, now we look at it and it's like, okay, that's a lot, but I can handle it. Me and my theta hat can handle anything. So the objective here then, just to recap, I need to find a way to lump together these things to talk about their joint contribution and their significance. These things to talk about their joint contribution and their significance, and these things. Because conceptually, these 3 right here are education. These 2 right here are working class group. And these 2 right here are age. So the lumping, new code for lumping is our new friend, contrast in SAS. We'll get to make friends with the others. I have 4 different contrasts here, trying to help you understand what these things are doing. The way that contrast works in SAS is that you list the slope that you want, followed by a 1, and you use commas to separate each slope. So this first contrast is something that I don't actually need to write. This is how I would have gotten the f-test for the model had it not been provided for me. It's all 7. Each slope followed by a 1, separated by a comma. Not a semicolon, but a comma. So if your contrasts are wrong, check your commas. If I forget a comma, like this, if you look at this, it doesn't jump out that this is obviously wrong, right? Because what's a comma? But what SAS would read this as, okay, she wants me to add together those slopes, like literally add them together. So we don't want that. There we go. So the 3 that I'm actually interested in are right here. I want to lump together the 2 slopes for working class, separated by 1 comma, the 2 slopes for age and age squared, separated by 1 comma, and the 3 slopes for education, separated by 2 commas. And this is a one-stop shop for giving you the f, semi-partial eta square, partial eta square, all of it. Just pops out. It's beautiful. In Stata, the new command is called test. And the analog to commas are parentheses. So that's one thing. Another set of parentheses for the second. And you'll note that rather than saying equals 1, I'm saying equals 0. Because literally what I'm testing is, what if that slope was 0? And what if that slope was 0? And what if that slope was 0? What if all 7 were 0? Is another way of saying, I'd like the f-test for the model R-square, please. So then to get the unique combination, the unique contribution of just sets of slopes, then I just list the 2 that I want. So like in the PowerPoint, if I want to test the contribution of slope C and D specifically to get the change in the R-square, I'd write C and D here. So there's what it would look like for age, and there's what it looks like for that. And I know we're about out of time, but I'll show you what it looks like in R very quickly. It's GLHT except with words. Isn't that an improvement? So in quotes is the interior part of what you want to set equal to 0. So here's how I would do all 7 slopes. List each, equals 0, in quotes, separated by commas. And here's how I would do working class slopes, age slopes, and education slopes. Now this is going to give me the F test, but I don't get the sums of squares. I need to do partial eta squares or semi-partial eta squares, so I got to work on that. But that will have to happen on garbage day because we're out of time. And now my hair is all screwed up. That's all right.
It's your last class. So.
It is, I know. I just had to get through office hours. And then I can have messed up hair for office hours. It's totally fine.
We know why.
We know. All right. Any questions before we call it a day? All right. Then I think that's a lovely place to stop. Homework is due Wednesday. Okay? Not Monday. Wednesday. So let me know if you need any help. Otherwise, have a good weekend. Thanks for being here. Peace out, everyone.